Every IoT device that connects over cellular has two things working for it. One, a trusted relationship with the network it serves, and two, a communication channel most security teams never think to examine. That combination is exactly what makes it dangerous. In this episode, I talk with Deral Heiland, Principal Security Researcher for IoT Technology at Rapid7, about a paper he and his co-researcher, Carlotta Bednar, just released. It's one that maps previously underexposed attack surface, the cellular modules embedded in IoT devices, from GPS trackers to alarm systems to autonomous vehicles and medical equipment. The research isn't about breaking into cellular networks. Rather, it's about something a little more unsettling. Once someone has physical access to a device, they can use that device itself, its authentication, its trusted network connections, its established communication paths, and use that as a pivot point for nearly everything else they want to do. Port scanning on internal networks, routing a SOC 5 proxy through AT commands, brute forcing S3 buckets shared across entire product ecosystems, all of it riding on the trust the device has already earned. And then there's the angle that Deral saves for the very end of our conversation, the one that keeps the supply chain security practitioners up late at night. If these devices can reach out, they can just as easily be configured to phone home, silently, over secondary cellular channels that most manufacturers don't even think to disable. This is a story about ongoing cellular IoT research. If you build, deploy, or secure a connected device, this episode is not optional. I'm Robert Vamosi. This is Error Code.
Yeah, my name is Deral Heiland. I am a principal security researcher for IoT technology at Rapid7. Best way to describe Rapid7 is a company that delivers solutions to companies that need to manage their security and their security risks, along with MDR, managed detection and response services, and also pen testing offerings.
I met with Deral at RSAC 2026. You may recall that I've talked with Deral before at Black Hat and RSAC, and he's been doing some interesting research on cellular communications. So we're going to talk about his latest paper, kind of a culmination of his work thus far. And I want to start by level setting for the audience, for anyone who's coming to this cold and not knowing about the previous episodes or his research.
The goal in this research initially, and we had talked about it before, was focused on understanding how cellular technology is integrated into IoT. You're seeing a growth of those devices, and this lives in the world of everything from transportation to medical to consumer grade goods, alarm systems, GPS trackers. But it was a focus on the cellular modules that exist on these devices and how they're integrated into the communication paths for IoT devices.
So there's a couple different kinds of cellular. And we're not going to be talking about LTE that we all have on our cell phones, right?
No, it's not. I would consider it not as advanced as those or the level bandwidth. The two classes of devices that we've looked at are NB IoT devices, which are high latency, low throughput, low speed, telemetry data, GPS trackers, things like that. And the other is the LTM class, which is higher bandwidth, full duplex, low latency communications, capable of moving video, voice, data, pictures, that type of stuff.
And what would that other category be?
See that in cameras, camera systems really big. I think it would also exist in larger scale telemetry driven stuff like automobiles, maybe autonomous robotic systems, things like that, where you need to move more data with a lower latency.
So Deral said it was full duplex. And that's the fun part of Daryl's paper, is the fact that the research looked at the malicious attacks that are capable in the cellular world.
Yeah, so the goal, like I said early on, learn everything we can about how these devices work, how they integrate in circuits. Once we figured that out, we noticed that, hey, this is potentially a pivot point. These devices live in a trusted ecosystem. There's some level of trust given to this device. How can we leverage that? How can we leverage how these devices function normal to be an attack vector. And that involved in interchip comms, ability to engage interchip communications from the IoT device's CPU to the cellular module. And in that communication path, be able to control, manipulate the cellular module to do our bidding for us or to pivot data through them.
So I want to qualify this up front. This requires hands-on. This is not a remote attack.
This is not a remote attack. We drove it from a couple different directions of ideas. One was when it comes to testing, and Rapid7 has an IoT pen test offering. How do we make it possible by understanding and building test models to give us the ability to look at the entire ecosystem instead of hit the cellular module and we're blocked. It's cell. We don't know nothing about that. Let's get rid of that shadow. And now we understand all the way through how this device communicates on an end-to-end basis now through this research. And now we can actually carry out tests through the device so that we can carry out attacks and test throughout its entire ecosystem, whether it connects out to cloud services, other internet services, back-end networks, database systems, anything this device has trusted access to, we can leverage all of that trusted access that the device sets up for us as a pivot through to them.
In the paper, Deral calls out 3 different attack scenarios. One is a TCP scanner. Walk me through that. What is that like from an attacker's perspective?
Okay, so the attack vector works on AT commands. So these cellular modules utilize a variation of the old Hayes-compatible AT commands, and they have a bunch of advanced commands, which we talked about in previous papers and in previous interviews, and be able to take those AT commands that have the ability to set up wall sockets. So we wrote just a simple script, very simple script that says, okay, I want you to set up a socket to a port at an IP address and then tear it down. Now we know that port's open. So now we can feed it an entire list of IP addresses, an entire list of ports, and it'll systematically open and close sockets and validate whether that device is up. So it's a rudimentary, and that port scanner would basically identify, hey, is there anything at the other end of this device's communication path that we could attack, somebody could attack?
Right. And the second attack in the paper talks about a SOC 5 proxy. A SOC 5 proxy is a flexible and secure way to route internet traffic through a middle server. To older proxy types, it's faster, more efficient, and supports authentication for added security. What makes it especially useful is that it can handle all kinds of data, both TCP and UDP. So it works great for things like streaming, gaming, torrenting, or getting around geo restrictions.
So we've written a number of different programs. So I was kind of challenged with that. It's like, okay, could we write a SOC 5 proxy, transparent style proxy that runs on a laptop that would communicate through serial to the interchip comms to the cellular module, use the AT commands to set up connections, tear them down, pass data, and pass data back to us. So basically route your laptop through serial comms using AT commands to attack anything you've identified with your rudimentary port scanner.
Once again, because it would be duplex, you would want to have the LT.
As a SOC 5 proxy, it's proxying another application. So the application you're proxying through would have to have the ability to be metered appropriately to handle the latency. An example would be like SSH. If I wanted to establish an SSH connection through this device, I could do that because SSH has a lot of settings where you can set timeouts and everything to large levels. So you can deal with those latency issues.
Right.
But not every program is going to be able to do that.
When we talk about latency, how severe is it? Are we talking nanoseconds, or can it get up into the seconds with IoT devices?
It can get up into the seconds on NB-IoT devices, so it can be pretty slow. It's not full duplex. The bandwidth, remember, it's meant to move telemetry data. But if you can meter things appropriately, there's no reason why you cannot route an application through NB-IoT. You just got to deal with that.
And then there's the last attack scenario.
Yeah, that was kind of interesting. Mainly it's just a pure proof of concept. We know most of the cellular modules have, most of the LTM have point-to-point tunneling protocol capability. Not all of them, but a lot of them do. And the challenge was, could we even carry that out? I know I pounded away at it for half a day, and I'm like, I don't have time for this. And Carlotta, my co-researcher, Carlotta Bidner, she took up that banner and she figured it out, got it fully functioning. Now, the speed throughput on point-to-point tunneling protocol, very slow, even on LTM. We noticed it was horribly slow. Things you could do in 10 or 15 minutes was taking an hour, as an example, because the overhead on the point-to-point tunneling protocol was significant.
Right.
And remember, we were routing this through serial.
Yeah.
Also, which added a lot more complexity to it. But that was mainly as a proof of concept.
Right.
Could this even be done? And she ended up writing a program that would completely rewrite the cellular module's functionality. It had to shut off USB ECM, which is Ethernet control mode, because you can only run. It was another protocol. You couldn't run both of them at the same time. So she figured out how to target the device and completely reprogram it to bring ECM down, to bring point-to-point tunneling protocol and move all the data through there. But it was driven as a proof of concept, and she did an amazing job making it happen.
So here we're talking about tunneling. Just want to be clear. Is this like IPsec tunneling?
No, not really IPsec tunneling. I'm thinking of tunneling because we're taking an exterior device through an IoT device to whatever it connects to. So we're like tunneling through the device.
Oh, okay.
That's how I'm using the term.
Okay.
So not necessarily from a protocol standpoint, but more of a functioning standpoint. We are tunneling through the IoT device to whatever it has trusted access to.
At some point in the paper, Deral talks about SIMs and eSIMs and how they lack authentication.
So that was based on previous research that had been published at Black Hat by a number of things. Sorry, I can't remember the name, but it's actually in the paper. We found that interesting because some of their attacks, they were actually able to steal SIM data and mimic the SIM or duplicate the SIM, and they were also able to pull the SIM out. An example was pull the SIM out of a telemetry unit on a car, move it over to a development board, and often those will connect through what's known as private APN, through a VPN tunnel into an internal network. And they were able to use some of that attacks to gain access to internal networks by pulling the SIM card. So when we started looking at research, well, we don't want to duplicate that. What we wanted to do is, what if companies go, hey, that's bad, let's add more security. So let's add some kind of authentication from the CPU. Let's add IMEI number validation, which is tied to the actual module that's actually on the board. So if you start adding those, pulling the SIM out to another system is going to fail if they add that level of security. So we wanted to get beyond that. We wanted to go, hey, let's just let the device do all that hard work for us. Let it do all the authentication, all the connectivity, all the validation, all the passwords, all the logins, everything it needs to do. And when it's done, we'll just use that as a tunnel.
So one of the things Deral is alluding to, and we've discussed this in a previous podcast, is this bootstrap, that you can use these devices to get in and then go to an S3 bucket, or you can go to something beyond the network itself, or you can get into the infrastructure.
Most devices connect over public APN. Most consumer-grade stuff go over a public APN. Basically dumps it on the internet. But devices that use a private APN actually hit the private APN, and it creates a VPN tunnel into a corporate network. In those cases, it's on a corporate network somewhere. It's connected to somebody's internal network, whether it's a DMZ or an open network, who knows. But once this device has done all that authentication, now we'll just use that as a tunnel, an access place. Now all of our tools are designed to leverage this device's ability to authenticate to whatever it needs to authenticate to.
So again, I'm going to level set for the audience that they understand that once we've done this, once we get access to the S3 bucket, how can we then exfiltrate any of that? We're not going to go back the way we came in because of the latency, because of the bandwidth issues.
It's going to come back.
It is.
It's going to come back. So in some demo videos we did in our presentation here, and we actually show it doing a brute force against an S3 bucket. And Carlotta wrote the program to do that. So it goes through it. You can set everything up, the bucket names, what you're looking for, a list of names you want to look for information, and just start brute forcing the S3 buckets. And our train of thought was that this device connects out. Well, this is not the only one of these devices on the face of the earth. If you have any IoT devices, there's literally thousands, tens of thousands of them sold how many of those share S3 buckets? Do any of them share S3 buckets? And this is the way to test that. So now we can go through that device and we can actually enumerate the S3 buckets on the internet, the ones this device is on,
Right.
or if we wanted to, we could use it to target somebody else. So nothing says you have to target this device's resources. You can target anything on the internet through this device. But the focus was, in our train of thought was, hey, this device is in a trusted ecosystem. How many devices in that ecosystem trust? As a pen tester, when we start testing like cloud services and internet exposed services or testing IoT devices, we're already interested in is like, I can get access to my data. Can I get access to anyone else's data based on that trust relationship? And if that's possible, then your ability to attack other components within that product's ecosystem become apparent in that particular case. And that's kind of why we did this. Now, the proof of concept tool out there currently isn't configured to use S3 bucket passwords or anything like that, but that's a quick change. And since we're inter-chip comms on these devices, not only can we use these devices as a pivot point, we can also listen to these devices when they initially authenticate. We can grab all their keys, passwords, certificates, and everything. Mm-hmm. So then we have the ability to reduplicate those in the attack channel.
So I'm beginning to wonder, could you, once you have these, move to a faster device, a faster way to exfiltrate?
That inter-chip communication captures, and what does that actually mean? In those cases there, if it's on the internet, we could literally take that off and go to a regular laptop and go over the internet for the most part. That data is available. So we knew that. And I think IoT pen testers are quite aware of that, because that's an attack vector we all use. We can go and we can dump the firmware and often find all those keys. Mm-hmm. For example, in this case here, we can now sniff all that communication in real time, and then we have the data also. But our concern was those elevated, more critical infrastructure devices, transportations, medical devices, the ones that don't connect just to the internet, that do connect over private APNs.
Right.
So we wanted to build a whole attack vector understanding and methodology for those higher critical devices. How would we attack those? Because we know we can already attack the internet. So this devices are only connecting to the internet. The risk there is lower. We have the device, we can get the data, we could do all those same testing. But if the device actually authenticates into some private cloud or private function, or they're doing it encrypted from the CPU like they're supposed to, and we can't capture it, because that does happen. And if that happens to be the case, those rare cases where they do good encryption and we can't get that data out, we can still ride through on the tunnel.
So I've been thinking of an analogy, and Deral can tell me if I'm wrong, but when NASA reaches out to, say, the Voyager 1 spacecraft, the latency there is something like over a day and a half in pulling that data back. It's extreme, but it kind of sounds like what we're talking about here. You're not going to get fast exfiltration through this process.
But when we get into the LTE-M devices, those move data between 1 and 4 megabits per second.
Okay.
It's pretty deep. Now, we do have serial bottlenecks. Serial runs on all the devices out of the box at 115/200 speed, which is kind of a common baud rate, but they have the capability of ramping that up to 4 megabits per second. So you can ramp the serial baud rate up to match the cellular comm rate and move data pretty quick if you want to. I mean, we're inside the device. We know how to talk to the cellular module. I have full control of that cellular module. I can make it do anything I want.
So it's the way of getting to the cellular module that becomes the bottleneck,
Hardware,
whether it be a UART, a USB, or serial.
Well, the USB is pretty fast.
So with these attacks outlined in the paper, how worried should companies be? I mean, we're talking about IoT pen testing. So there's a subset of all companies that are doing that today, right? And then there are the companies that are getting these pen tests. How concerned should they be about these devices leaking critical keys to their S3 buckets or data?
Yeah, and in that case there, I challenge companies out there, start doing threat modeling. Look at my paper, start doing threat modeling. Is this a potential risk within your product or your product's ecosystem.
Right.
And if you think it is, then test for it. Either do your internal testing or external testing, ever how you do it, and have somebody test those attack vectors. Are they valid? Are they impactful? If you build critical infrastructure devices or things like that are cellular based that do connect over a private APN, where they're connecting their internal, for heaven's sake, test this. Test it to make sure that this attack vector is invalid before you start shipping 10,000 products around the world that connect into your internal network.
Right.
And then we have mitigations. If these devices are connected into your internal network as part of their ecosystem, then do good security at that point. Remember, these devices shouldn't be able to go in and port scan your internal network. They should, if it connects in, it should only be able to connect to a single port or a port that it needs to move data in and out of to a single IP address. That's it, nothing else. And then validate cross-sharing. So if you have 10,000 devices out there, or all 10,000 of these devices have some level of shared trust between them, also watch the data. What kind of data is coming through? Is this the data your product's supposed to be sending you? Pay attention to that. We're in this AI age now. And when we start thinking of autonomous robotic systems, that AI drives these, and they improve their processes and their functionalities that impact the entire ecosystem of every device out there. If I own one of these devices and I decide to poison your data through this attack method, what does that look to all your products' ecosystems? Are they all using that data? How would that affect you? So it's like segmentation, logging, and validating behavior analytics on your network. The standard network stuff that you do now, but hyper focus into that communication landing point on your network from these devices.
And then with threat modeling, you're not going to be boiling the ocean. You're not going to be looking at every single IoT device. You're going to focus on the ones that you assume have some control and either confirm or deny and then move on from there.
So when you start thinking about consumer devices, my level of risk kind of go down. At that point, I wouldn't worry about, hey, if I own this device and I can steal my own data out there, it's really not a threat. But are you sharing API access, authentications to anything from multiple devices? Then you may want to separate that so they don't do that. Because if you say, hey, all my devices are going to have this really good encryption and authentication, but then they all land on the same bucket or the same location, and you're using some kind of other flagging to segment them, well, I'm sending and controlling the data. I can bypass that. So if everyone's landing in the same place, then I have access to everyone else's data. So you want to separate data sharing or separate authentication. So everyone authenticates separately. So each one of them has their own, what was that called? Not really a private VPN, but I can't remember. But basically the concept that they all land in their own location. They don't share any data between them. And that would be consumer grade stuff. Now, as this risk goes up, as you get more advanced technology and what they have access to, and that's where all the other critical security best practices come in place.
Right. It sounds like security controls will mitigate a large part of this.
Exactly. But unless you know it's taking place.
Right.
And there's always this weird and inherent trust. It's like it's a machine that's talking to another machine.
Sounds like security controls can mitigate a large part of this.
What could go wrong? Well, Deral can go wrong. If I have one of those machines, then I have access to everything it has access to.
So are there any real-world attacks on the cellular structures that we've talked about?
I don't know of any attacks taking place. I think the research we have done, I don't want to say it's completely unique, but I haven't seen a whole lot of other work published in this area or through this process. So the goal is to kind of get ahead of that, build that knowledge, and that's what we're doing here. We're trying to build the knowledge so everyone can start thinking maybe better security. How do we make it better? It may be come down to the point where the manufacturers of cellular modules start thinking about how do we add other security methodologies into our products to make sure that not the consumer, but the people using our products in their products have a better list of options for better security.
Would that involve the authentication that we just discussed?
It may be authentication. It may be added encryption. It may be the ability to turn off some of these unused services. Because when we're talking the LTM devices and NB-IoTs, they have two communication channels potentially to the device.
Right.
One's used, the other one's not used. The one that's not used, I can use, or we can use, or somebody can use for actually controlling and manipulating and sending actual data through that device. Have the ability to actually disable that completely and not make it easy to re-enable it. The other option is can we encrypt everything from the CPU, or at least have the ability to do that? Right now, none of the AT commands are actually encrypted. And none of the modules we looked at have the ability to encrypt or encode the AT commands. So I can sniff those also. And then maybe password protected device. Say, okay, when the device fires up and makes these configurations, and at that point, the only way I can make changes to the device, I would have to have that password before I could start manipulating and turning services on or off. Those may be things that we need to consider, potentially end up in product, which I think would be great. It would be great improvement across the board. And the only way, in my opinion, to eventually get there is the knowledge. Do the research and go, hey, this is what we're seeing. Now, how do we fix it? All right. And I don't have all the answers to that.
So one of the buzz phrases at RSAC 2026 is non-human identity. And that communication can be considered a device being identified on a network.
It's the whole machine-to-machine communications. There typically should not be any human interaction in there.
So I wonder if there was anything that I haven't covered in the paper that Deral wanted to bring up.
I think the interesting thing also, we talked mainly with some of the tools were the serial communication. But in the paper, we also talk about USB. So most of the more advanced LTM devices use what's known as ECM, which is Ethernet control mode or Ethernet control model. Basically, if you connect over USB to the cellular module, it shows up as an Ethernet port.
Oh.
So in one of our attacks, we actually spliced a USB multiplexer into the device. And once the device authenticates out, we're able to throw a switch. It switches over the multiplexer to our laptop. It gives us an Ethernet port and an actual IP address, and we can route through it just like a standard Ethernet.
Okay, that's freaking cool. And that was just serendipity?
No, because remember, there's two channels we know exist on that, USB and Ethernet, serial. So the goal was the serial is easy to figure out in the AT commands. The USB and how to connect in and dealing with the electronic aspect of that in circuit is a fairly complex protocol. There's electrical standards on how USB even routes across a circuit board, and being able to solve those to avoid impedance mismatch issues, skew, because you got two opposing lines on USB. If one line's longer than the other, you end up skew and it'll start failing and airing out. Being able to match all those to splice in a multiplexer was probably the most complex. In the paper, we go through a lot of the details, even some basic math concepts around that. The math concepts I lay out there are not engineering level math concepts. They're because engineers are more strict guidelines. This was guidelines strict enough that you don't impose any kind of impedance issues, but still work. And that was our goal.
So again, this is part 3 of an ongoing series of projects that Deral has been conducting. Is there a future, or is he moving on to other research?
Well, I'll probably move on to other things because I'm always have everything changing on my plate and what we need to do or look at. It doesn't mean this is completely dead. There are some other interesting vectors in this also that we discuss. I think I mentioned in the paper. I can't remember if I mentioned in the paper, and that's deal with because we talk about data going from the device out and hijacking that. But I've also in various talks alluded to the fact that can go back the other way. So doing implants in the supply chain on critical infrastructure devices, potentially could mean that these devices could phone home to somebody nefarious over that unused communication channel in the cellular module and take command control, monitoring, all kinds of things. So we haven't discussed that a whole lot at all, but it's something I think we still need to think about. And I'm not sure if I'll do any more work in that area or what that means. But that's always been an interesting concern that we need to probably address also.
And it sounds like we need to really shut off that second line of LT communications to be secure.
It's very difficult to mitigate all the risk completely out, but you can add certain levels of complexity. So the people that are doing it are going to have to work much harder and find ways around all of these mitigations. And I think that's the better solution. We're never going to take it all away, but how do we make it hard?
Right.
And like you said, being able to shut off that secondary channel and not make it usable at all would probably be the first step.
I'd like to thank Deral Heiland for coming on the show and talking about his continuing research on cellular in the embedded space and how it is an attack surface that may not be recognized by all security practitioners, but needs to be. Hey, if you're enjoying Error Code, tell a friend. I'm sure there are other people out there who like narrative information security podcasts. And I'd really like to hear from you. Go to errorcodepodcast.com to get more details. And tell me what you like, and even what you don't. I've got some great episodes coming up. We'll have more on Volt Typhoon, Salt Typhoon, and hacking utilities supply chains. Subscribe today. I don't want you to miss out.